Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today I'm very pleased to have Vinod Vaikuthanathan visiting to speak to us on side channels and clouds. So now I've gotten over my big hurdle for the day, so pronouncing his last name. So we're very pleased to have him visiting. He's currently a postdoctoral fellow at IBM, and he did his PhD at MIT with Shafi Goldwasser in 2009, where he won the Best Dissertation Award from the Computer Science Department. So thank you, Vinod.
Thanks, Kristen. Before I start the talk, I have to tell you that Kristen told me before the talk that she wants to ask me a lot of questions. I really want to encourage you guys to do the same. Let's make this interactive. So the topic of this talk is side channels and clouds, new challenges in cryptography. The development of cryptography has always gone hand in hand with the emergence of new computing technology. Whenever there is a big change in the way we do computation or think about computation, it has always led to problems and challenges for cryptography, and ultimately we have faced these challenges. We have managed to come up with new techniques in cryptography. In fact, we can see, if you look back at the history of cryptography, we can see a number of examples of this, such as the development of automated ways of doing cryptography, of encrypting messages. For example, the Enigma machine of the 1930s, the invention of public key cryptography in the 1970s, and so on and so forth. Today, in the 21st century, we stand at the brink of another big change in the way we do computing. A lot of computing these days is being done on small and mobile devices, which are computing out there in the world in an environment that we do not necessarily trust. Whereas we used to think of data being stored and programs being executed in a personal computer, sitting right in our office under our control, these days we do a lot of our computing on devices such as laptops, cell phones, RFID devices, and so on and so forth. The problem with this change in the way we do computing is that these devices store sensitive data, and they're just out there computing where the adversary, the attacker, has an unprecedented level of access to these devices and control over these devices. He has a lot of the devices are becoming closer and closer to the adversary, and that's making it much easier for the adversary to carry out his attacks. The second big change that we see in cryptography, in computing, is that the amount of data that we need to store and the amount of computation we need to perform on this data is becoming so huge that the end users are not willing to do all of it themselves, either because they simply do not have the resources to do so or various other reasons. Instead, what they do is they outsource storage and computing to big third-party vendors such as Microsoft, Google, Amazon, and so forth. This trend is called cloud computing, and it is again a big concern in terms of cryptography because we are putting our data and programs out there away from our trusted personal computers. This new computing reality poses two new challenges for cryptography, which will be the focus of my talk. First of all, in cryptography, we traditionally think of cryptographic devices as black boxes. In other words, what this means is that the assumption is that the only way an attacker can access the cryptographic system is by giving it input and receiving the output of the computation. What's really going on inside the device is, he has no clue what's going on. The real world is quite different. In fact, it turns out that there are various mechanisms by which computing devices leak information to the outside world, not just through input-output access. In particular, an attacker can avail of a large family of attacks called side channel attacks, which reveal extra information about the storage, about the data stored inside the device and the computation being performed. Side channel attacks utilize the fact that physical characteristics of computation, such as the amount of time for which a particular program runs, the power consumed by running a piece of software, or in fact, something non-invasive, such as the electromagnetic radiations emitted by the computation, emitted by the device during the computation, all these physical characteristics leak more information about the computation than just input-output access. And this extra information leakage has actually been successfully utilized to break many existing cryptographic systems. So one thing I want to say before I go further is that these attacks are not completely new. They've existed for well over a couple of decades. What makes them particularly acute and interesting in this context is the physical proximity that the attacker has to these devices. And this is a result of our, the new sort of computing reality that we're facing. Another point I want to make is that these attacks are not just theoretical attacks. They're actual attacks on implementations of standardized crypto systems such as RSA, advanced encryption standards, and these have been attacked very successfully using side channel attacks. So this is sort of a real concern for us. So the first challenge number one that I will address is, can we protect against this kind of information leakage? Can we protect against side channel attacks? Okay, so that's number one. Okay. The second challenge appears in the context of cloud computing, the context of security in cloud computing. The general setting of cloud computing is one in which there is a client and a server. The client has some input data and she wants to do some computation on the input data. And the point is that she may not have enough resources to do the computation, or might otherwise be unwilling to do this computation herself. So what she does is she sends the data across to the server, which does the computation on her behalf. This is a very general setting, and specific examples of the setting are specific familiar examples of the setting are the context of searching the internet, using Bing, for example, to search the internet. But this is also interesting in the modern context in a more general scenario where the server performs an arbitrary computation on the input data. So first of all, the client may not be willing to disclose her entire data to the server. Why would it, right? So the client demands privacy of her data. And one way to achieve privacy of her data is for her to encrypt the data and send it over to the server. Don't send the data in the clear, encrypt it. But now we are in a little bit of a problem, because what the server gets is encrypted data. It doesn't even see what's inside the ciphertext, and yet it's supposed to execute the program. It's supposed to perform some meaningful computation on the underlying data. So the question is, can we reconcile these opposing goals of privacy and functionality? So in more concrete terms, our challenge number two is, can we compute on encrypted data? Okay. So these are the two challenges I'm going to address in this talk, and the talk will go in three parts. In the first part, I will show a mechanism to protect against side channel leakage. In fact, this is a hugely active area in cryptography at this point. Many models of how side channels behave, and many constructions of cryptographic primitives that are secure against side channels. In this talk, I will tell you about a simple model for side channels and a solution, and a construction of a particular cryptographic primitive that is secure in this model. And this is joint work with Adiya Kavya and Shafi Golwasser. In the second part of the talk, I will describe a mechanism to compute on encrypted data. And this is done using a very powerful cryptographic primitive called a fully homomorphic encryption scheme. And this work is joint with Martin van Dijk, Craig Gentry, and Shai Levy. And finally, I'll tell you about my research philosophy and a bunch of open questions and future directions. Okay, so this is the structure of the talk. And probably this is a good point to stop, see if everyone is on the same page. Okay, wonderful. Okay, so let's jump right in. Part one, how to protect against side channels. The traditional approach to handle side channel attacks has been to address side channels as they come along. In other words, for for each particular kind of attack, design a tailor-made solution that handles this attack. So that has been the traditional way of looking at this problem. And this can be done in hardware, namely manufacture specific types of hardware that protect against specific attacks. You can modify programs so that they resist particular kinds of attack. So one sort of little drawback with both these solutions is that they are usually ad hoc, and they don't come with a proof or a guarantee that they actually do the job. Solutions have also been explored in a sort of a higher level setting, in an algorithmic setting, when people have considered leakage of specific bits of the secret. So let's leak the first bit and 50th bit and 100th bit and so forth. This is a very specific kind of leakage. Again, people have explored this in a number of works. So this general approach of solving side channels has two problems. One is the scalability of this kind of solution. So every time you want to protect against a new side channel attack, you have to incur the cost of building in a new type of countermeasure. And in other words, the cost of your solution grows as the number of side channels that you want to protect against. Yes?
Just curious about your distinguishing between algorithmic and software attacks. There's a lot of overlap. I'm not sure I'd really distinguish them that well.
Sure. So the line is a little bit thin in that case. But what I mean by software is that I take a specific program. So one approach that people have explored to counteract timing attacks is to make sure that the program runs for the same amount of time on every input. Right? That's not an algorithmic. So the line is a little bit thin, but good. So the first problem with this line of attack is its scalability. The cost grows as the number of side channels we need to protect against. The second, more subtle and probably more serious problem is the composability. To roughly explain this problem, the problem is that if I build in a solution that protects against one side channel, and build in another solution that protects against the second side channel, who said that the effects of these side channels won't cancel each other? The question is, do the different protection mechanisms work well with each other? And that may not be the case. In fact, people have done a lot of work in studying the effect of these countermeasures, the effect that they have on each other. Okay, so there are a couple of problems with this traditional specific approach to counteracting side channels. What we will look at today is a modern approach. The modern approach is to say, let's step back and let's try to come up with a model that captures a wide class of side channels and design a solution in this model. And if your model captures a large class of side channels, the solution will be secure against all these attacks as well. And this approach was advocated and pioneered by Micali and Raisin. So in other words, instead of looking at each of these side channel attacks one by one, what we want to do is we want to define a model of the adversary that interacts with the system, and this model should capture all these attacks in one go. And once you come up with this model, you want to construct cryptographic primitives and prove that they're secure in this model. Yes?
Before the new wave of side channel attack, I think the military had a simple approach to side channel attacks. Keep the crypto stuff in a very secure location and don't let anybody in. And except for timing attacks, it seems to be a pretty good idea.
So it is, but the attacks still don't prevent people measuring the electromagnetic radiation that come out from my cell phone, like when I'm walking around, for example.
Well, that's a cheap cell phone. If it were a serious tempest, it would have some Faraday cage.
But then you don't get portability, which is the whole point.
True.
Yes.
Right.
Yeah.
So
Probably for
cell phone and carrot
$5 you could get portability too.
So I put my phone on a $5 Faraday cage and I try to punch the buttons through the grill.
Okay, anyway, keep going.
But good point. Okay, good. So this is the general approach that we want to take. And this is as I said before, this is a very active, very recent and very active area of research, and with a number of models and matching results. Aside from the results that I mentioned before, many other researchers have come up with various different kinds of models and constructions of cryptographic primitives. What I'm going to talk about today is one specific result, the work with Adi Akavi and Shafi Golbasser, in which we propose a simple model and the construction of a particular cryptographic primitive that is secure in this model. So that's what we're going to talk about today. So the model we propose is called the bounded leakage model. And the starting observation to this model is that if you allow the side channel to leak an unbounded amount of information, there is really nothing you can do, because the information could be the entire secret contained in the device itself. So one sort of necessary condition that one condition that seems to be necessary is to put a limitation on the amount of information that the side channel leaks, and that's our first restriction. We say that the amount of leakage is less than the length of the secret key, and in fact it's a parameterizable quantity. The larger this amount is, the more secure you get, and so forth. This is the first requirement that we pose on side channels. The second observation is that if you allow the side channel unlimited computing power, then it can break the crypto system itself, right? I mean, there's no way you can protect against such a side channel. And that leads to our second restriction. We say that the side channel should be the computation done by the side channel, which is an antenna for electromagnetic radiation or your oscilloscope for a power attack, is polynomially bounded. That's our second restriction.
Is it really enough to have leakage just be less than the length of the key?
No, a lot less than the length of the key. In fact, it's a parameterizable quantity.
Okay, good.
I should say that it's possible to, this is a very basic model, and I'm presenting this because of simplicity. In fact, it's possible to relax both these conditions, in particular the information limitation, quite a bit, and I'll be happy to talk about this one-on-one. Okay, good. So this is the model, this is the sort of the abstract model that we will work with today. Yes?
Wait, so the first restriction, a restriction on the adversary or on the...
It's a restriction on the, so if you think about side channels, there are two entities, right? One is me, I'm the attacker, that I'm using a particular hardware device to get some measurement on the computation. So there are two entities here. One is the attacker, one is the device. And the restriction is on the device, on the amount of computation that, amount of information that the device gives me and the amount of computation that it can do. Does that answer your question?
So you're saying that this will only work if the device just naturally leaks less information than the key?
That's right, absolutely. And in fact, you can see that if the device leaks, the amount of information that it leaks is more than the length of the secret key, it could just leak the entire secret key itself, right? Potentially. So, good. So, good. So this is the model that we'll work with today. And the rest of this part of the talk, I'm going to use public key encryption as my example primitive. And let's refresh our mind about what public key encryption is. In this setting, there are two people, Bob and an Alice. Bob wants to send a message to Alice privately over a public channel. And the way he does it is by letting Alice choose two keys, a secret key and a public key. Public key you publish, a secret key you keep with, Alice keeps with herself. And Bob has a mechanism to use the public key to encrypt the message, send it over to Alice on the public channel. And Alice can use her secret key to decrypt. So it's a simple, very simple setting. And what the attacker can do, the attacker that we will look at in the setting is an eavesdropping attacker. Right? I mean, that's the most basic model of that's the most basic attack that you can perform on a public encryption scheme. The attacker gets access to the public key. It's out there in the open, so you can look at it. It looks at the ciphertext because it's going through a public channel, and it tries to gain some information about the underlying message. And the security requirement, the classical security requirement is that the attacker has no information about the underlying message.
Your keys, they're already leaking bits of information, right?
Public key?
Well, because it's got the MIT marks on it, right? Those are your office keys.
Oh boy, okay. Aside from that, no.
Fair enough.
I'm surprised that you can see it from here.
Yeah, it's a 60X or something, right? I don't know what building that is, but
It's a Faraday cage.
It's correlated.
yeah.
Oh boy.
Just Josh.
We want to talk about the bounded leakage model, and the change that we make to the security game is very simple. We, instead of, in addition to letting the adversary get the public key and the ciphertext, we also let him ask the decryption oracle, the decryption box, for a leakage function f. So this is the leakage function that's computed by either the oscilloscope or your antenna. I mean, this is one that models both these leakages. And as a result, he gets back the function f applied on the secret. Right? So this is a very sort of simple extension to the classical security model.
So f is polynomial time bounded. Oh, I
Click.
just, okay. There.
Okay. So obviously, following our discussion before, we need to have two restrictions on the leakage function f. One is that it has bounded output length, and this is sort of a parameter. This is sort of a sliding scale. The more the output length is, the more the leakage is, and the better your security gets. The second restriction is that the function is polynomial time computable. Okay, so this is the sort of the concrete model for public encryption that we'll talk about. Okay, so now we have a model. The question is, are there encryption schemes that are secure in this model, that protect against this class of attacks? So let's first look at well-known encryption schemes that we know and love. So unfortunately, it turns out that the RSA encryption scheme is insecure against bounded leakage. There are a number of results that show that if you leak a small constant fraction of the secret key, you can break the entire crypto system. So RSA is out of question. As for the El-Gamal encryption scheme, there is no explicit attack that breaks the system with leakage, but there is no real guarantee or proof that it's secure either. So unfortunately, these two systems not good for us. What we show is that a newer class of encryption schemes, based on mathematical objects called lattices, are in fact secure against bounded leakage. So these are not, the mathematical basis for these systems is not factoring or discrete log, but it's a different kind of object called lattices. So we show that an encryption scheme proposed by Regev is secure against leaking any constant fraction of the bits of the secret key, say 99% or 99.99%. And subsequently, in work with Dodis, Goldwasser, Kalai, and Pikert, we showed that a different encryption scheme based on lattices also has this property. The interesting thing that I want to point out is that these encryption schemes were not explicitly designed with leakage in mind. They were designed for a completely different purpose. It just so happens that the leakage resilience is built into them. Okay, so that's what we show. And following our work, a number of other constructions were shown to be leakage resilient as well, some of them based on more standard assumptions, such as the Diffie-Hellman assumption, and also a sort of a class of constructions based on what's called hash-proof systems. They were also shown to be secure against bounded leakage.
Who are the authors on this? BHH?
Good. So this is Dan Bonnet from Stanford, Shia Levy, Mike Hamburg, and Rafi Ostrovsky. Good. So there are all these constructions. In the rest of this part of the talk, I'm not going to focus on any of these specific constructions, but instead we'll step back and ask the question, what is it that makes these schemes leakage resilient? Is there some kind of underlying structure or a principle behind these schemes, which makes them secure against these attacks? In fact, I will show two principles, two ideas, such that if an encryption scheme satisfies these two principles, two conditions, then it's automatically secure against bounded leakage. In fact, all these encryption schemes that I showed in the previous slide actually satisfy these restrictions. So you can think of this as sort of a way to explain why these schemes are leakage resilient. The first idea, the first property that I require from an encryption scheme is that given a public key, there are many possible secret keys. In fact, I will require that there are exponentially many possible secret keys for any given public key. So if you're used to thinking about RSA or El-Gamal, this is a sort of a foreign concept. Because in RSA, the public key is a product of two primes. The secret key is its unique factorization. So although you can't compute the secret key efficiently given the public key, it is uniquely determined.
The secret key of RSA is the decryption exponent, in which case there are many equivalent keys.
Good. So you can add a multiple of yes. So I'm gonna get to it in a minute. Okay. So this is the first property we require. And of course, the encryption algorithm, when it encrypts a message, it has no clue which secret key the decryption box contains. It could be one of these exponentially many possibilities, and therefore correctness of the encryption scheme requires that any of these secret keys decrypt the ciphertext to the same message. In fact, the message that the ciphertext originally encrypts. So in other words, all these secret keys are functionally equivalent. They all decrypt the ciphertext to the exact same message. And yet, even though they're functionally equivalent, we will show that partial information about any single secret key is totally useless to the attacker. So let's actually think about this idea, sort of step back and think about this idea for a little bit to answer Josh's question. Right? So you can take any encryption scheme that you like, and you can make it have this property. So you can take the secret key and pad it with a bunch of random nonsense. Right? I mean, so the number of secret keys grows, but we haven't really done anything, right? So this idea by itself is not particularly useful. What makes it useful is the second idea. And the second property that I require from the encryption scheme is that there are two distinct ways to generate a ciphertext. One is the way that Bob uses to encrypt his message. This takes a message, uses the public key, and computes a ciphertext. So this is what Bob does in the real world. The second way to generate a ciphertext is what I will call a fake encryption algorithm. The fake encryption algorithm is fake. I mean, no one ever executes this in the real world. It's just an artifact of the proof. It's just a sort of a mental experiment that exists because we want to prove this scheme secure. So a fake encryption scheme is a randomized algorithm that takes nothing, no input, and just produces a random ciphertext. And the ciphertext behaves very differently from a real ciphertext, in the sense that if you take the ciphertext and decrypt it with any of the possible exponentially many keys, you will get a different message every time. So if I take a random one of these secret keys and decrypt this ciphertext, I will get a random message. So functionally, the ciphertext behaves very different from a real ciphertext. Yes?
You're going to show, I guess, sufficiency of these, but presumably nothing's known about their necessity of these two ideas, or you'd have an answer for all.
No, I don't. So in fact, a couple of slides before I mentioned that El-Gamal is not known to be secure in this setting. So it turns out that El-Gamal encryption scheme does not satisfy either of these properties. But we have no clue if it's secure or not. So I'm not sure that these ideas are necessary, but this is one way to achieve security.
And for the lattice stuff, because they're all shortest vector based, and you have a lot of equivalent short vectors. I mean, is that where you're getting this from?
So just a brief sort of overview of these lattice solutions. So in the lattice-based encryption schemes, the public key is a point in space, in an n-dimensional space, and the secret key is any lattice vector that is close to this point. So depending on how you define close, there could be an exponential number of points that are close, and that's what contributes. And of course, it still doesn't explain why the scheme satisfies this other property, but just to give you an idea. Okay, good. So the fake ciphertext behaves very differently from the real ciphertext, and yet we require that if I see a fake ciphertext on one hand and a real ciphertext on the other, I can't tell which is which. So fake ciphertext is indistinguishable from the real ciphertext. So even if you know the secret key, even if you know a single secret key.
Oh, a single one. Okay.
So if you know
the real one will decrypt to the same thing with different secret keys, but the other one won't.
Won't. So you can tell. But if you know a single secret key.
I got you. I believe that. Yeah.
Good. So this is the second property we need. And now I'm going to show that if you have these two properties, that's that. You get leakage resilience. Okay. So the first step in the way to see why this works is to look at the fake world and the fake ciphertext, right? The fake ciphertext obviously contains, it was generated without the knowledge of the public key or message. So it contains no information about any message whatsoever. In fact, the fake ciphertext decrypts to a random message under the choice of a random secret key. But this is what happens when the adversary is given just the fake ciphertext, right? So what if it's also given some amount of leakage from the secret key? Okay, so let's look at that. Let's say he gets 1 bit of leakage from the secret key, right? So originally, from his view, the number of possible secret keys was exponentially large. All these like huge amount of secret keys. If I get 1 bit of information about the set, that narrows down the set by a factor of half. So the number of possible secret keys is reduced by a factor of half. 2 bits, right? I mean, it becomes a quarter. And if I get a bounded amount of information about the secret key, there is still quite a bit of possibilities that are left in the left as the secret key. And of course, each of these random one of these secret keys decrypts to a random message, and therefore still the attacker has no clue what the message is. Okay, so far everything happened in the fake world, and we don't even care about what the fake world is, right? But the key thing to observe is that a ciphertext that happens that's produced in the fake world is indistinguishable from a ciphertext in the real world. So the adversary is not going to know the difference if it gets a fake ciphertext or a real ciphertext, and therefore it has no information about the message either. Right? It didn't have any information about the message in the fake world. Why would it have any information in the real world? That's that. I mean, that's the end of the proof. Right? And that actually finishes what I wanted to. I just told you about a model, a simple model for side channels, and a way to construct a public encryption scheme that is secure in this model. So that finishes my section on side channels. Is there any?
Well, supposing you. This is it's a big thing. Supposing you corresponding cipher in plain text, the real thing, would that help them at all?
A new ciphertext. Yeah. Potentially. So this is a sort of a stronger attack. The attack that you're mentioning is a stronger attack called a chosen ciphertext, or I guess a known ciphertext attack. Yeah, potentially it could, but I think, again, okay. Don't hold me to this. But I think I can show that this scheme is secure against a known ciphertext attack, ciphertext message pairs, and that's simply because it's a public encryption scheme, right? Yeah. I can construct messages in ciphertext by myself. But a chosen ciphertext attack is a different issue, and this may not actually be secure. But we can take this off. Yes.
How do I know if my system only leaks a very small bounded amount of information?
That's an engineer's problem.
That's exactly.
Okay, if I put an antenna at your smart card,
yes,
you're leaking continuous data over it, even over a bounded amount of time. How do I know that there's no bit in there?
How do you know that the leakage doesn't sort of uniquely? You can't recover the unique secret key from. So I'm going to borrow John's answer. Say that this is an engineer's problem, but
your motivation for the talk was all these countermeasures that engineers put in there.
Yes.
They're heuristics, and they don't really add any formal proof to what it is that you're doing, and that we're going to avoid that problem.
So one way to look at this solution is that if you can guarantee to me that the amount of information leaked by this particular attack is bounded, I'm going to show you a provable way to protect against this attack. So really, you should think of the solution as a combination of a hardware countermeasure and an algorithmic countermeasure. You give me the guarantee that the amount of information is bounded. Here's the solution.
It's not unreasonable. Imagine it's just a bounded channel.
I have a couple of different answers to your question. Maybe we can. Okay, so this is what I wanted to say about side channels. Let's move on. The second part is how to compute on encrypted data. So again, let's remind ourselves of our motivating example. There's a client and a server. The client sends an encrypted data to the server, and the server has to perform computation on the encrypted data and send back the encrypted result. This makes sense in various specific contexts. For example, encrypted internet search, which it turns out that for specific instantiations of this problem, there are already sort of tailor-made solutions that solve these cases. For example, searchable encryption is a cryptographic mechanism that solves encrypted internet search. But what we are really concerned about today is performing general computation on encrypted data. A cryptographic tool that is really helpful in this general context is called fully homomorphic encryption. That's what I'll talk about for the rest of the talk. Good. So, yes.
You're talking about privacy of the data submitted by the user, not the data sent back to the user, correct?
Well, so the question is, what does it mean for? It could be that we want to protect the program against. So it could be that the client doesn't know what program the server is running, and I want to sort of hide this fact from her. But that's sort of a different concern that we're not going to focus on.
In your case, you care about effectively blinded results, right?
Yes.
That's what the goals are. Sort of, but
You do it the other way.
okay, yeah. Yeah.
Well, another way to look at another way to answer your question is that the computation on the encrypted data is performed without the knowledge of the secret key, right? I mean, it's a public computation. Anyone can do this. So the information that the encrypted result leaks cannot be any more than what the original ciphertext leaks, because I'm performing some public computation on the encrypted data, right? So, okay, good. So this is the problem that we're concerned with. So we're going to model a program, an arbitrary program, as a Boolean circuit, right? I mean, so if you go down to the most basic level, you can write any computation as a combination of exclusive OR gates and AND gates. So I'm going to write this as a big Boolean circuit. So I'm going to look at exclusive OR. Exclusive OR is really addition in a field of size 2, and is multiplication. So that's an equivalence I'm going to use. So what is a fully homomorphic encryption scheme? A fully homomorphic encryption scheme is a scheme where you can compute the AND function on 2 encrypted bits and the exclusive OR function on 2 encrypted bits. You can add and multiply encrypted data. And because you can write any computation as a combination of AND and OR gates, if you can do both these, you can do everything, right? So that's a fully homomorphic encryption. What do we know about a fully homomorphic encryption scheme? This sort of concept was first defined by the name of privacy homomorphism by Revest, Adelman, and Dutazos already in 1978, when they didn't really have a candidate scheme that satisfied their definition. So it was such an insightful sort of act of foresight that they defined this without even having the candidate scheme. And their motivation was actually the modern motivation for constructing these schemes, namely searching on encrypted data. What we know so far are limited variants of homomorphic encryption. For example, the RSA scheme, we know that it's multiplicatively homomorphic. For example, if I give you encryption of one message and a different message, I can compute the encryption of the product of the 2 messages. That's something you can do. The El-Gamal and the Goldwasser-Mikhaili encryption schemes are additively homomorphic. You can add encrypted plaintext, but you can't multiply them. There are also mechanisms that compute very limited classes of functions on encrypted bits, namely quadratic formulas. But the real question is, can you do arbitrary computation on encrypted data? And that has been open for nearly 30 years. Until last year, Craig Gentry constructed the first sort of instantiation of a fully homomorphic encryption scheme. This construction was based on very sophisticated new mathematics based on ideals in polynomial rings. So a fully homomorphic encryption scheme is a really very powerful object, and this lets you do a lot of very nice, useful things. The question that Gentry's construction raises is there a simple and elementary way of achieving fully homomorphic encryption? I don't want to have to learn algebraic number theory to understand algebraic X. So the question is there an elementary construction of this object? So in other words, the question we want to ask is, what simple mathematical objects can you both add and multiply that both permit addition and multiplication? So what we show is the construction of a fully homomorphic encryption scheme based on integers. Namely, the operations, the basic operations in this scheme is just addition and multiplication, plain addition and multiplication of integers. No ideals, no polynomial rings, just simple operations.
Found in some way? Integers mod something?
Integers mod something, because
How big is the thing? Because the penalty for the Gentry function really frightened me.
good.
You know, I'm more afraid
So-
of an Avogadro's number cost function than of having to learn new math.
The answer is kind of unfortunate. If you're frightened by the cost of Gentry's function, you'll be really frightened by. But the point is that the point I'm trying to make is that you can improve on a construction only if you understand it, right? You have sort of a good idea of how this encryption scheme behaves, and therefore, what we should do is construct simple, elementary, encryption schemes. Good. So we show two constructions, one based on integers, and the security of the scheme is based on the approximate GCD problem. The second construction uses addition and multiplication of matrices, and this scheme is not fully homomorphic. It can only evaluate a limited set of functions, namely quadratic formulas. And the security of this is based on standard, well-studied lattice problems. So what I'm going to talk about is the integer-based construction. Good. So let's sort of jump in to the scheme. So first of all, what I'm going to describe, we've been talking about public encryption all over the place, but what I'm going to describe to you is a secret key homomorphic encryption scheme. Namely, to encrypt a message, I need the secret key, and I decrypt the message, decrypt the ciphertext using the same secret key. So that's the setting. In fact, this setting is already useful in the context of cloud computing because the sender and the receiver are the same entity. So how does the encryption scheme work? Well, the secret key is an n bit, where n is pretty large, n bit odd number p. Okay, so that's the secret key. Okay. How do I encrypt a bit p? I'm going to talk about sort of encryption schemes that encrypt a single bit for simplicity. How do I encrypt a bit p? I pick a large multiple of p, let's say q times p. So q is a very large number. I'm going to pick a small number, a small even number, 2 times r, and I'm going to add all these quantities together with the message. So the ciphertext is q times p, this large number, plus the small noise term, 2 times r, plus b. That's the ciphertext. Okay? How do I decrypt this ciphertext? First of all, if I take the ciphertext, I have the secret key. I'm the decryption algorithm, I have the secret key. If I take the ciphertext and take it modulo p, what I get is the noise term. It's 2 times r plus b. In fact, the key thing to note is that I get the exact noise term. I do not get 2 times r plus b mod p. I get that number by itself. Right? That's an important thing to note. And now, once I have this noise term, I can just read off the least significant bit, and that's the decryption algorithm. Okay, so this is the entire encryption scheme. Any questions? Questions, comments? Good. Wonderful. So this is the encryption scheme. What I didn't tell you is how to add and multiply encrypted bits. So that's the next thing I'm going to tell you. How to add and multiply encrypted bits. And in a high level, addition and multiplication works because if I take a ciphertext and another ciphertext and add or multiply them together, the noise term is still going to be small. Assuming that the original noise is really small, the noise terms are not going to grow by too much.
Would
Yes?
the number be not leak when you encrypt successive messages using the same key?
No. So that's part of the assumption. So the assumption is that if I give you many, the approximate GCD assumption is that if I give you many near multiples of p, like large multiple plus noise, it is indistinguishable. You can't recover p. That's the assumption. So good. So addition and multiplication works in a high level because the noise terms do not grow by too much when you add and multiply numbers. Okay, so let's look at it more concretely. Let's take two ciphertexts. one encrypting a bit B1 and the other one encrypting B2. And addition of the underlying bits is done by simply adding these two numbers, as integers. So when you add these two numbers, I get a multiple of p. I get a noise term, which is slightly bigger than the original noise because I added two of these things together, plus the sum of the two bits. Right? So now if I take this sum of the two numbers mod p, and I read off the least significant bit, I get the exclusive OR of the two bits. So that's that. How do you multiply? Essentially proceeds the same way, except that it gets a little bit more, the algebra gets a little bit more complicated. So when you multiply two ciphertexts, I again get a multiple of p, plus a small even noise. It's much bigger than before, because if you start with a sort of a n-bit noise. Good. So I started with an n to the half bit noise, an n to the half bit noise, and what I get is 2 times n to the half bit noise. That's the resulting noise, right? And if I take this mod p and read off the least significant bit, again get the product of these two bits mod 2. Okay. So the homomorphic operation, homomorphic addition and multiplication, is simply adding and multiplying the underlying integer ciphertext. Josh, question.
By John's
No, you get n-bit noise, not
Yeah, this
two.
is R1 times R2.
R1 times R2 is n bits times 2 n bits, right? So am I missing something?
R1 is square root of n bits.
So square root
Square root.
square root of n bits, sorry.
N bits. Yes.
Never mind.
Got it. Thank you.
Good. So it's still
Don't make that mistake.
What sort of N is it if you want serious security?
That's a good question. So it depends on how secure we believe this approximate GCD problem is. I don't have a good enough answer to you, and well, actually, I don't have any answer to you. So you have to study this problem and see how difficult it is. Some of which we do in the paper, but we don't have a concrete recommendation for what the security parameter is.
So the approximate GCD problem was just introduced a year or two ago, or what was the
Good. So this problem has been known in various different sort of forms and shapes before. So if you look at it a little more carefully, you can see that this is a variant of the simultaneous Diophantine approximation problem, which is saying that if I give you many fractions, I give you many fractions, and you have to find me a fractional number which approximates each of these sort of many numbers that I give you. So this is a problem that was fairly well studied. In fact, Jeff Lagarius has a work on it from as far as 1982, and people have studied this problem for a while. So the name was introduced by Howe Grave Graham like 5 years ago.
I suppose you can get to this very quickly, but you can only do a few multiplications.
Oh, good. So, okay, good. So you see that the least significant bit is the product of the middle. Oh, great. Okay, good. So clearly, this scheme has two problems. One is that if I multiply two ciphertexts, the size of the resulting ciphertext grows, right? And essentially, it grows. Essentially, when you compute a big program on the ciphertext, the resulting ciphertext is as big as the size of the program itself. So if you think in terms of the cloud computing example, the receiver gets this huge ciphertext. Just reading the whole thing takes it as much time as computing the program. So this is a huge problem. I'm not going to talk in detail about how we solve this problem, but the rough idea is that we give the server another near multiple of p, and every time you do a homomorphic operation, you take this mod, this near multiple. So I'm not giving you any extra information because it's another. So instead of giving you 100 near multiples of p, I'm giving you 101 near multiples. So hardness of the problem doesn't change by much, but it decreases the size of the ciphertext. The more serious problem is that the underlying noise in the ciphertext grows whenever you add or multiply numbers. This is a slightly more serious problem to handle, and in fact, the first thing that we observe is that we can do a limited number of additions and multiplications already with this basic scheme. And then there is a way to bootstrap this limited additions and multiplications to get computation of an arbitrary circuit. This is a very beautiful technique that Craig Gentry introduced in his original construction. So putting these two things together essentially solves our problem. Okay, good. So this is QED, all I wanted to say, right? Any questions? Good.
How important is that? So I think the bound on R1 was the square root of n bits.
Yes.
So how important is that to be able to increase it, say, or how flexible is it?
So you can make it a polynomial in n, let's say n to the 0.99, and you will still get, so the larger you make that noise, the larger your noise grows when you do homomorphic operations, the smaller the number of homomorphic operations that you can do with this basic scheme. So you have to, so amount of noise dictates the amount of homomorphic operations that you can do. On the other hand, if you have a larger amount of noise, it's conceivable that the underlying problem is harder, right? So there's a trade-off here. The smaller you make the noise, the easier the underlying problem becomes, and the more the homomorphic operations you can do. So square root of n is sort of an arbitrary number which lets me do log n multiplications. That's the sort of threshold I want to reach.
Log n? Because
order of log n.
Okay.
Order of log n. Okay, good. So that's that. In the rest of the talk, 2 slides, I want to tell you a little bit about my research philosophy and tell you about a couple of open questions that this work leaves behind. So I think cryptography is an exciting field to work because it both takes practical problems that arise in practice, and solves it using very exciting mathematical techniques. So this combination is what makes, for me, what makes cryptography a very exciting thing to do. What I told you about today is 2 applications, 2 exciting applications that we solve using cryptographic techniques. The first is security against side-channel attacks. So both these fields are very sort of new fields. They're just in their infancy. There's a lot of work to be done. A big question that arises in the context of security against side-channel attacks is the following. I showed you a particular construction of a public encryption scheme that is secure against side channels. The question is, the big question is, can you take any program which is not necessarily secure against side channels and immunize it against side channels? Is there a general way of transforming any program to a leakage-resilient program? And that's like, and I want to do this while not killing the, for this to be practical, I want to do this while not killing the efficiency of the program. This is, I think, a very big question in this field. Number 2, again, the big question in the context of computing on encrypted data is how efficient can you make the fully homomorphic encryption scheme? The scheme that I presented to you is a little bit slow. So it's polynomial time, but it's a big polynomial. So asymptotically, I think we did a back of the envelope computation. We didn't even care to sort of optimize the exponent of the exact polynomial. So I think the number that we came up with was n to the 8. So in other words, if executing a program takes k steps, executing this under the encryption takes n to the 8 times k steps, where n is the security parameter.
The size of the universe?
Sure. Okay. So the really big question here is, can you do this? Can you take this algorithm and make some improvements in the implementation? That might already bring down the complexity quite a lot. And then the question is, can you design like completely different schemes which are dramatically more efficient? That's the big question. One thing that I didn't get to tell you about is my work on the mathematical foundations of cryptography. So a lot of these works use either explicitly the encryption schemes that I developed based on lattices. Lattices are geometric objects that look like periodic grids in space, but they embed very hard problems, very hard computational problems. And this is a very new sort of mathematical field that we have based cryptography on. And it turns out that the schemes that we develop in this context are useful in both protecting against side channels, and also the insights were useful in constructing the homomorphic encryption scheme. So this is another sort of big set of problems that I'm interested in. And that's that. questions?
Your integer lattice scheme has a bit of the flavor of the end-row schemes that were used a few years back. Is there any relation, or is it just pictures?
So there is no formal relation that I can prove yet. One sort of superficial difference is that the end-row scheme, in fact, all lattice-based schemes use n-dimensional lattices, and here we are just working with integers. Right, so that's a very superficial difference. But the real answer to your question is that a lot of the insights are the same in constructing both these schemes, but I don't know of a formal connection.
I guess, I'll ask at this point, this is probably something we need to talk about offline. I'd love to get a better sense for how the smoothing works to keep the error terms down. And I imagine that's more than a slide or two.
Yes.
Okay.
Yes. In fact, sort of handling these two problems that I mentioned is quite. I mean, it's 15 full minutes of a talk. Okay. So I'd be happy to.
Yeah, that won't suffice.
And was that, I was going to ask about your estimate of the n to the 8th. Would that comes out of those details?
Where that comes out? So it comes out of the details. So if you look at the so the security parameter that we work with is the size of the noise, right? So let's call that k, which is square root of n. So the prime that I need to pick is of size k squared, right? And it turns out that this problem is actually easy if the multiple that I choose, the multiple q that I choose, is too small, right? So I need to pick that to be sort of the square of this size of p. So that's k to the 4th. And then when I do this bootstrapping process, that already adds a square of this number. So that's k to the 8th. I'm not sure if this explains anything, but the complexity grows very fast when you put all these steps together.
It's still the size of it sounds more like the size of the thing grows, but you're actually saying the number of steps grows. So
that's probably not, the number of steps grows too, and that's probably not apparent from what I described, but once you do this bootstrapping process, the time required to process every gate is essentially k to the power 8, the size of these numbers. So I can explain this offline.
Another thing, following up on one of Brian's comments in the first half of your talk, so does it actually, instead of the shortest vector problem, does it actually reduce to the closest vector problem?
It's not the closest vector problem, and it's something that looks like the closest vector problem. The closest vector problem says that I give you a point, and you're supposed to find the really closest lattice point. The problem that I'm looking at here says that I give you a point in space, and you're supposed to find some close. Yes, some close point within a certain radius. There are exponentially many close points, and I'm supposed to find one of them.
Other questions?